And somehow this is not large enough. Sorry about that. This is the no, I'm using the new Keynote. I've never used it in presentation mode before, and it's probably trying to be less smart. Well, this is not meant to be. Sorry, just a moment. This is what happens if you upgrade the operating system and then Apple decides to change everything, how things work. And especially, yeah.
I upgraded mine and it suddenly altered my calendar, like deleted random things from it.
Oh, nice.
Yeah, I thought that was high quality.
So, okay, I think I know what's going on. Okay, just don't. Sorry. Okay. So this should work. Okay. So I believe that's a little bit more readable. Okay. So today we are going to do a little bit of theory and a little bit of proofs. So I hope that's nice and relaxing coming from the midterm. You'll be getting the midterm exam back at the end of the class. And yeah, after that, I mean, have a look at it. Have a look at what went well, what maybe didn't go so well. And I mean, basically, think of the midterm, you know, let's say professor's wheel to intimidate the students. Think of it bug report from a compiler, right? Or, you know, overall a bug report. As in, it'll tell you the things that you got right, and it'll tell you that maybe you want to up a little bit more. Right. So the main point of this midterm is, okay, sure, you need to. I hope that nobody's going to be in serious trouble there. Is to tell you which things you know, which things you maybe don't quite know as well as you thought you did, and to try to do this in a moderately objective fashion. Okay, so look at the scores. Don't be super upset if they're not so amazing. If they're really good, you know, be happy about it. And basically look at the things where you probably want to read up a little bit more. Okay. So what we are going to do today is a little bit more foundational. So this is, you know, this is one of those lectures where it's really good if you know them, and it's most important that you know qualitatively what types of statements you can get, as opposed to the very specific theorems to statistical learning theory. Otherwise, the main thing you really care about is just to have an intuition can inject. So with that out of the way, let's look a little bit at what happens if we want to, let's say, estimate probabilities. So let's start with something very, very simple, right? We start with a binomial distribution. I mean, this is like the simplest thing you could do, right? You have heads and tails. And so, you know, after you observe from that distribution, you can ask, well, what's the data likelihood? And so you would basically have pi, let's say heads. The data likelihood for that very specific sequence is just, you know, pi to the n1, that's the number of heads, times 1 minus pi to the n0. Now, that's a little bit different from, you know, what's the likelihood of observing any sequence that has that number of n1s and n0s, because then you need to actually look at the corresponding combinatorial coefficients for. That's what. Okay. So now, once we have that sequence, we can ask, what is the best way how I could choose this parameter pi? I mean, everybody here, I guess, knows what to do. Namely, you take the number of times you see by the total number of draws. And you say that ratio is now an estimate for the probability of seeing heads, right? So if I toss my coin 100 times and I see heads maybe about 42 times, then I know that 42% might not be a bad estimate for the number of for the probability of seeing heads. Right. So you might ask, where does this come from? Because I mean, this is completely intuitive and everybody does it anyway. So let's actually do this very simple thing now in excruciating detail. The excruciating detail is here. So what I've done is I've parameterized pi in a very, very awkward way. I've parameterized pi as e to the theta divided by 1 plus e to the theta. Okay. Now this looks completely crazy. Why on earth would I do this? Right? The reason is that before that we had a constraint where pi had to range between 0 and 1. Instead, I'm going to make my life easier, and I'm just going to pick a unconstrained expression, because I mean now I can pick theta to be anything from minus infinity to plus infinity, which will cover the range of values between 0 and 1, and I'll just optimize away at it. So in some cases, this actually makes my problem a lot easier. So getting rid of constraints by variable transforms is a not uncommon technique for solving optimization problems. Okay. Because after all, unconstrained is easier than constrained in general. So let's then write out, p of x parameterized by theta is just the product of those probabilities. And you can immediately also see that 1 minus pi is 1 minus e to the theta divided by 1 plus e to the theta, right? This is 1 plus e to the theta minus e to the theta divided by 1 plus e to the theta. And of course, this goes away. And as soon as that happens, I just have 1 theta. And that I can write as e to the 0 times theta. Therefore, I can just write the entire expression as the product over e to the theta xi divided by 1 plus e. Remember, so it's not completely crazy how on earth I dreamt up this formulation. Okay, so let's take logs. And what we'll get is theta times sum over the xi's. That's basically number of hits. Minus n times log of 1 plus e to the theta. Okay, so this is equation line number 2. So we're just taking the log of it. Now, if I take the derivative, well, nothing easier than that. I mean, after all, theta is a scalar. I get this expression here. And then solving for theta, well, it gives me this condition here. So I get that this ratio, which is exactly what I said p of x equals 1 to be, is given by, 1 over n sum over xi. And that's where I can stop now. Now, the interesting thing is that I basically have an empirical average here. And I set this to be the probability estimate. And so, of course, the question is, how many of those xi's do I need for this number to be reasonable? Right? So how many do you guess? How many do you think I should at least use before I can even remotely trust this number? Who votes for 1? Who thinks 10 might be okay? How about 100? How about 1,000? Right? How about 10,000? So, yeah, and essentially as I cranked up the numbers, more and more hands went up. And there's a reason why you didn't all decide at the same number, because after all, it depends on how accurately I need it, right? If I just need to get that probability estimate down to, maybe, let's say it's 40% plus minus 20%, I don't need a lot of data. If I want to write to 40% plus minus 0.1%, I will need a lot of data. And the time when you raised your hands was very much a function of, what accuracy level you presumed was a good one. Okay? And so the question is, of course, can we get a handle on, how this accuracy level depends on how many observations I see? Before we do that, let's just have a quick look at another distribution. So here's a discrete distribution. Let's say, for instance, nationality of people here in the room. And of course, I've not covered everything, but, well, whatever. So now, again, you write out the same equation for the data likelihood. You write out the same exponential form, like so. And you get the same result out of it again. I mean, it's just a slightly more involved derivation, but it effectively amounts to the same thing. Namely, you count the number of times, let's say, the nationality is, well, Indian, and you divide by the total number of counts. Okay. So these are empirical averages, right? So one thing that I did then is I figured, well, okay, let's take a distribution where I know exactly what the limit is. Well, so I took a dice in Octave. So in other words, I took, a random number generator that produced integers from 1 to 6 with equal probability, and I let it run. And that's what I got. So what you can see is, so this is 60, 120 draws. And the red line tells me where I should be. The blue lines are the actual counts. And as you can see, well, it's not quite perfect, right? So now the question is, can we actually get guarantees on, how large these deviations are going to be with some, confidence? And so what the rest of this class is all about, figuring out how large these deviations can be, maybe as a function of, size of the domain, and various tools to do this. Okay. Any questions so far? Okay. So basically, we want to understand this graph, and we'll do that. Now, why would I care, right? So you care a lot because let's say you have 2 drugs, and you want to find out which drug is better. And maybe there already, 1 or 2% better means, 1 or 2% fewer people die. So you really want to get that probability estimate really right. Or let's say you have a semiconductor fab, so where they make, chips like the chip in your laptop. They usually have a sequence of, up to 1,000 different processing steps. And in each of those steps, something could go wrong. And it's not like you run this process and then you get, 100 out of 100 chips being properly working, but, you'll have a higher or a lower yield. So if your fab is working very poorly, you might have a yield of 10%. And if your fab is working well, it's going to be quite a bit higher than 10%, but nobody will ever tell you. But you have levers and, configurations and processing steps where you sort of kind of have an intuition of what should happen, but in the end, you really need to measure it. And so you want to find out, if I run the process with, procedure A versus procedure B, which one works better. Or a famous example is for user interface design, right? So if you think about websites, they figure out based on, the things that they do, what the user engagement is. So one of the famous examples is how the Google Blue came to be, as in the shade of blue that you see on Google. That particular shade of blue was one of about 150 different candidates of blue that they tested. And so what they did is they basically partitioned the user population, maybe not everything, but some sliver of the user population, into 150 groups. And for each of those random groups, they gave them a different shade of blue. Otherwise all the results were the same, just that shade was different. And they let their systems run as they would, regardless of everything else. And then they measured the user happiness, which is some secret formula of number of how much people click and how much they look at things and God knows whatever. But basically they measured happiness. And to ask, how long do I have to run this experiment before I can reasonably confidently which color it is, right? And so for that you actually need statistical confidence bound, because it could be simply one of those things works a lot better in the beginning and then later on not, and maybe that was just a fluke, right? So this is quite important when you design user interfaces. So the picture up here is one that's taken from how to do A/B testing for webmasters. And essentially, the question is basically how much skin or whatever you show in order to get user engagement. And those three gentlemen essentially provide the tools for doing this. So we'll focus on a part of that slide. So here's what we do. Right. So suppose I have some random variable, we have some probability measure, and I am interested in the expected value, right? Special case is, if I have a discrete probability mass, well, that's fine. I just sum things up. If I have intervals, same thing. And so now, let's say I draw those xi's identically independently from p. So this is often referred to as the IID assumption. Pretty much everything that we've done so far in this class is assumed to be IID, independently and identically distributed. It's a horrible assumption to make in practice. So for instance, if I look at user behavior, probably today people behave a bit differently from tomorrow, from the day thereafter. And if you build a model that doesn't really take this into account, well, your relevance suffers. Nonetheless, it's an okay model. Or for instance, if I look at handwritten digits, well, maybe the way how people write the first digit in a zip code is a bit different from the last digit, right? So it's not quite correct, this assumption. But often it's good enough that this approximation will give you good enough results. So on top of that, it just makes the math a lot simpler. So for most of this class, we will assume that the data are IID. In practice, for your research, you should actually check whether this is truly the case. And if you have a reason to believe that this is substantially violated in practice, you should probably cater for that. And there are models like, for instance, Markov models that actually allow you to deal with this easily. Then I'm interested in these quantities. So I'm interested in what's called an empirical average. So our training error was empirical average, right? And if you think about it, in the homeworks, sometimes your empirical average was very good. You had a very low training error. And then you uploaded it. And then the expectation, which is drawn from this, was quite different from the empirical average. So now what we want to be able to do is some confidence that this is close to its expectation. And well, for this distribution, you might be checking stuff like this. So of course that'll depend a little bit on, how wiggly this function is. So for instance here it has a range between 0 and 1. So therefore I know that by default this is probably going to be easier to do than if the function, has a range between 0 and 1,000,000. Okay. So let's make the following practical case just to see a little bit how it works. So let's say a gambler rolls a dice 100 times and he counts the number of times that the 6 occurs, right? So you've probably played a game of dice with some friends and that one guy just happened to have a lot of luck or a lot of bad luck. And you start wondering sometimes, maybe something's wrong with the dice. And so let's say this guy is a little bit unlucky and he only gets a 6 11 times. And of course we know that the fair number would be 16.7, right? Or something like that. So the question then is, this dice tainted? And this is, a slightly abstract. Things like, is your ad campaign working? So you're showing ads. Are the users really attracting more users? Is this drug really working? Or, is the new page layout truly better? Or maybe I just got lucky. And so let's actually work out what the probability of seeing 6 at most 11 times is. Okay, so I need to sum over the probability of seeing 6 at most 11 times. So I need to sum over the case that I see a 6 only once, no time, once, twice, up to 11 times, so P of I. Now, okay, so we can just write it out. So this is I out of 100, 1/6 to the I, 5/6 to the 100 minus I. And since they are quite manageable numbers, I just wrote that on my computer, summed up over, in this case, 12 numbers, and I get about 7% out of it. Yeah, you want to be a little bit careful about 100 factorial. That will go bad. But other than that, it's very easy to work out. Okay. So what you see is that the probability of seeing 6 at most 11 times in 100 trials, that probability is about 7%. So we shouldn't be too alarmed yet. I mean, you just get a little bit unlucky occasionally. So let's get a bit more of an intuition of what's going on. So what I did is I drew 1,000 times from a dice. So what you see on this graph here on the log scale is number of draws. And wherever you see a plus, that's where I drew a 1, a 2, and a 3, and so on. And the red curve is the average, which is 3.5. That's the mean that you would expect. Is the average that I get by averaging over everything up to this point, right? And just a linear interpolation, right? So what you can see is that initially this deviates quite a lot. It actually crosses once or twice slightly, but then as we converge, it gets closer and closer to this red line. And so the question is, can we get a nice predictable envelope that tells us within which those things are? Does somebody have an idea what the rate of convergence is? Yeah, okay, so you're all going to learn something new. That's great. So the hint is this rate of convergence is like 1 over square root number of samples. Okay, and we'll actually derive this. So we'll derive a whole bunch of equations that initially look very intimidating, but actually if you look at the way how to prove it, it's not very hard. And you'll learn some useful techniques. Whatever we don't get through today, we'll cover on Monday. So, yes?
The line is always below the...
Yes, and that was just unlucky. So that's the other thing. I mean, you could read some meaning into this, right? And when you do experiments and you see stuff like this, you will probably, unfortunately, read meaning into this that simply isn't there. And later on, I'll show you a graph just like this with 5 or 6 draws. And some of the lines will stay below, some will stay above, some will cross. And you can actually also work out the probability of crossing. But that's a little bit harder.
some of the numbers are different than others, would it still be the same rate of convergence?
So the rate would be the same unless you have some very, very specific properties. So there are special cases where the rate can improve from 1 over square root n to 1 over n. That usually happens when you have constraints on one side, and sometimes you take you take the minima of some functions and so on. So there's a couple of cases where you get a faster rate, but in general, the 1 over square root n is something that you're stuck with. So the only thing is that in some cases, you may have a transition between two regimes, where initially you get a faster rate until you get to the point where you're just averaging. And as soon as you're in the averaging regime, 1 over square root sample size is really the thing that you're stuck with. It's very, very hard to engineer beyond that. So there are some very, very cool techniques that let you do this for some special cases, but in general, that's what you're stuck with. So the key question then is, can you get better constants? Okay. So let's first actually prove that this thing converges, right? And that's already, not an entirely trivial thing. So if I have a random variable, xi, with mean mu, and I take the empirical average, then the weak law of large numbers says that in the large sample size limit, the probability that the empirical mean deviates from the mean by more than epsilon is 0, or in other words, so the probability that it doesn't deviate by more than epsilon is 1. This doesn't, so this holds for any epsilon. That's a little bit different that, in the limit, this will actually converge to mu. This is the strong law of large numbers. We're actually going to prove those. So this means convergence in probability. So just whenever people talk about weak or strong laws, in one case they just mean, well, the mean doesn't deviate from its expectation by more than epsilon and for any epsilon you can find something. In the other case, you can actually say that the quantity converges. Now, here's the graph that I promised you before. These are now 5 sample traces. So exactly the same experiment as before. And I just drew, 5 different curves. And the blue envelopes are exactly the 1 over square root sample size envelopes. Actually, it's the variance divided by square root of sample size. And you can see that this is a pretty good envelope to contain all of this. And we're going to work out how we get there. So this is, of course, it's more than just say, hey, things converge, but it tells you how rapidly they. Also, what the limit distribution is. So, yes.
So what was the difference
What was the difference between those two between any of those two curves?
No, can you go back one?
Okay.
These two.
Okay. So one tells you just, well, for any given interval, if I draw enough observations, at some point the average is going to be inside the interval. The other one says, as my sample size goes to infinity, the empirical average will truly converge to the expectation.
So the difference is at any specific point, the probability of being in the interval versus the probability of ever leaving the interval at any point in the future.
So the first one will contain the second one?
No, the weak law is weaker than the strong law. So that's how it's easy to remember. Yep.
Shouldn't the weak law should be something like there exists a capital inside that holds in place of maybe because infinity should strong law should as well.
So the other way around, what you want is that so you pick an epsilon. And then I will tell you that as I get more and more observations, will ever go outside this epsilon, probably will go to 0. But you basically pick the epsilon problem. Whereas there, for that convergence to happen, you basically need to know that, well, you're not going to leave this ever again. So that's why it's slightly stronger. So for the purpose of things, these two statements. So basically, what you need to take away from the weak and strong, unless you have a particular pathological, the empirical averages will converge to the expectations. Okay, and we'll get to also some pathological cases, like the Cauchy distribution, for instance, which doesn't even have a well-defined mean. Which sounds weird, but yeah, you can design such things. So the central limit theorem is stronger yet. And for that, you need to have certain additional conditions happen. And basically, what is that if I take a variable, where in each individual one has variance sigma I, and then the sum over them minus the sum over their means, this quantity rescaled by the inverse variance will go to 0, right? But this rescaled will now converge to a normal distribution with 0 mean and unit variance. So basically for IID random variables, we know that the sum of the variances, well, it's just, n times sigma, right? Now, if I then divide this, right, I get the suitable normalization. So there you can see we have the 1 over n, we have the square root n, so these things just, cancel out. So you get exactly the 1 over sigma times square root n rate. And here we have xi minus mu. So this gives me exactly the 1 over square root n convergence. Okay. Now let's prove this thing. Okay, so for that we'll need a couple of tools, and they're useful in their own right, but let's go through this. And they're actually very intuitive what they do. So the first thing is Slutsky's theorem, and I'm not going to prove this. Take a little bit of time and effort here, and the result is actually very intuitive. So let's say I have two random variables, xi and yi. And the yi's converge to a constant in the limit, and the xi's do something, right? Then if I take a function g of x and y, and this function is continuous in all x and is a continuous function for all g of x at c, then g of xi yi converges in distribution to g of x and c. So in other words, what I can do is I can take essentially dependent. So to repeat it, if I have two random variables, a well-behaved x, then I can take essentially the limits independently and then look at the function of the limits of those two random variables. So if you want to see a proof, I think Spiegelhalter actually has a rather nice proof on one of his lecture notes. Okay, so this is something that we need. So g of xi yi converges to g of x and c. So this is a convergence about the random variables. So, these are not necessarily specific numbers, so the difference is that, each time you look at it, you get another random variable back. Yep?
Can you clarify what it means for a random variable to have a value at its limit?
So that's very easy. Basically, in the limit, it converges to constant. So let's say I have some random variable like this average before. So this one, for instance, would have this property, the sample average in the limit will converge to 5.
Okay, so the average value of the samples converge.
Yeah, basically I can treat it as a constant in the limit. And I don't have to worry about any other interactions. So
it's stronger than saying that the average converges, right? It's stronger than saying that the mean of the random variable converges, right? The random variable loses its
So basically, we'll get to that in a moment, just on the very next slide, is that if I have a function of two random variables, and I know that one converges and the other one does something else, then I can focus on that random variable that does something else, and the one that converges, I can just plug in its limit. And that's what makes life really easy. Okay. So let's take a random variable xi that converges to b. So this is called the delta method. And we'll need both of those and the characteristic functions. So there are 3 tools that we'll need to prove all of those things. There are tools that are useful in their own right, so it's go through them. Probably one of the most math-heavy lectures in this class. So, but after the exam, we'll not be asked to do it in the exam anymore because there's no. So, I hope that minimizes the pain and the panic. Okay. So, what I'm interested in is x converges to b. And I'm going to pick an inverse squared, and I basically know that, well, if I pick those suitably, then I will get the convergence to a normal distribution with 0 mean and some variance sigma. Okay. So now let me take some function g that's continuously differentiable for that limit, for some limit b. And I'm interested in what happens to g of xi. So have you ever done physics experiments? Have you ever done sensitivity analysis of your results? Right? So that sensitivity analysis was something like, hey, we got some result. Now let's see what happens if we jiggle the variables a little bit, our observations. How much would our result change? That's effectively what we are doing here. And the delta method is basically a formalism for showing that in the limit, just looking at the derivatives at the result that I got is good enough. Okay. So in short, this g of xi inherits the same convergence properties as xi had. So what we're going to prove is this blue line, namely that the same coefficients that we have before, those an minus 2, an to the minus 2, so this is just a normalization, of g of xn minus g of b will converge to a normal distribution with 0 mean, that's good. And now where the covariance sigma is just, modified by the chain rule, right? This is really just, the second derivative at b. Okay. So this is a really super useful result if you have functions of random variables and you want to know how they behave in the limit if the random variable has nice convergence properties. So a lot of asymptotic analysis for statistics uses these kinds of tools. So let's just do a Taylor expansion, right? So I can Taylor expand. And what I get is that, g of xn, I can write it, as g of b plus, and then I have xn minus b times, now I have the gradient of g at some location psi n. So this is just standard Taylor expansion. This is, you know that the psi has to be somewhere on the line between xn and b. This is exactly what we're going to exploit because we know that xn has to converge to b. So this poor guy gets sandwiched in between the xn and the b, and that interval gets smaller. And so this has to converge to that gradient at b. Right? So therefore, we get this as a gradient. And so then what we have is we have a random variable. Now, some vector transposed xn, where before we had this originally. And if I just multiply this, then I know what happens to the covariance, right? So remember, if I have some random variable x, and I have some matrix A, and I know that the expected value of x is mu, then I know that the expected value of ax, just by linearity, is a times mu, right? And furthermore, I also know that the expected value of, if I know that xx transposed is sigma. Okay, I'm assuming it's centered, so I'm just skipping over a few things. Then I know that the expected value of a times x transposed a transposed is, of course, nothing else than a times the expected value of x transposed a transposed, and I know that I can just plug in sigma here. By linearity of the expectation, I can pull multiplication, and that's what I've done here, right? Because this just becomes, my matrix A. This is my random variable that I'm interested in. And then I just apply Slutsky to now get this result for the delta method. And I can see that, this g of xi is asymptotically normal if the xi was already asymptotically normal. Okay. So to recap, I have some function, I have some random variable that's well defined, and I know its properties. And I'll take some function of this random variable, and if the function is not too unpleasantly defined, basically if it's continuously differentiable, then in the limit, this function of that random variable will behave just like an equally well-defined random variable itself. So, for instance, something like this here wouldn't do. Because what you would have is that, as things converge to 0, let's say, there's no smooth transition between the left and the right. And that's actually non-trivial then to, prove properties for this. Okay. Any questions about that so far? I know this was probably one of the more mathematical parts of this class. So don't worry, we'll get more applied next week. So this means, converge almost surely, so now the next thing that we need is the Fourier transform. Who has never used the Fourier transform before? Okay. Read up on this absolutely insanely awesome tool. No, actually, you have used the Fourier transform before. Okay. Who's ever used an MP3 player and fiddled with the equalizer? Okay, I think everybody has, right? This is doing the Fourier transform effectively, right? You have an audio signal, and you split up that signal in low, medium, high frequency and different frequency ranges. And the Fourier transform is basically the mathematical device the audio signal and maps it into corresponding frequency portions. And the really awesome thing about Fourier transform is that it goes both ways. That I can turn my signal into something that's given by frequency components, and also the phase relative to that. So basically where what the I can turn this back into the original function again. So I can basically use it to analyze things. Then maybe I can reweight things. This is what the equalizer does. And then it actually does an inverse Fourier transform to get the new transformed signal back. Fine.
Under which conditions can function F is Fourier transform convertible?
Okay, what are the conditions for f? Well, usually you go and define the Fourier transform on L2, so basically square integrable functions. But you can actually look at slightly more general conditions, in which case then you basically need to worry about which Banach spaces you're dealing with, and you basically need to then only apply these functions to the dual Banach space. So if these are questions you're very interested in, they're really cool questions, you should take a function analysis class. I think Geoff is actually going through this in his reading group right now. You should attend his reading group. He's doing really awesome things there. So
We'll have to get a bigger room.
yeah, but basically this has a lot to do with dual norms. I don't think we have time to go into this here. We will probably cover this in the advanced optimization class next semester. So there you'll have optimization over function spaces, norm duality, and actually those dual norms have exactly the same. They don't just share the name with all this duality stuff that we did before. This is actually what happens if you go from standard inner products where things are symmetric to inner products where the left and the right argument are now taken from different spaces. So you've probably heard about the L1, L infinity duality, and this goes much more general. Okay. Zooming back to this, here we just assume that everything is nice in Hilbert spaces and so on. So I'm skipping over a lot of the pathological cases that lurk in the corners to get the main idea across. So Fourier defined exactly as this integral. The inverse Fourier transform looks the same, just that rather than e to the minus I, whatever, you have e to the I. That's it. This is the transform. So the first useful thing is that the inverse Fourier transform is the inverse of the Fourier transform. Duh. Okay, good. You want to know that, right? The second thing is taking derivatives amounts to multiplication in the Fourier domain. Now this is really cool, right? Well, why does this happen? Well, let's just squint at the upper right. So I want to take the derivative with regard to x. So I, do that. And then I can just perform partial integration. So in other words, I exploit the fact that the integral of f prime g is the same thing as the integral of f g prime, same thing as f g between them with the corresponding brackets minus the integral f g prime. So in other words, rid of the integral of the derivative y, but then I have to integrate the exponential, which is really easy. We get this, and then I'm done. So where did my bound? Well, basically I had to assume that this function at the limit minus plus infinity vanishes, and that's what I had to do anyway for this function to be square integrable. Yep?
Doesn't that work even if f is not differentiable?
Yes, it does work even if f is not differentiable, and then you have to do a bit more work. So basically, if you want to, but then you have to ask, what does it mean to take the derivative of a non-differentiable function, right? So I'm leaving all those ugly bits and pieces in the corners aside. Fun?
Pi to the minus d over 2 should be n.
Yes, n equals d. So on this slide, n equals d. Okay, so So now everything's correct again. Yeah. Now, the other really cool thing is that if I have a convolution of two functions, then in Fourier domain, this amounts to the multiplication. This is super useful because if I want to compute the convolution, so you've probably all heard about the FFT, the fast Fourier transform. The fast Fourier transform on a length L signal takes time. If you've never seen the FFT, go to Wikipedia, open your laptop right away, look it up. It's one of those amazingly cool algorithms. It's basically divide and conquer. And look it up, it's gorgeous. Okay, so you'll enjoy it if you've never seen it. Okay, now, the point is, this is L log L time. In general, a convolution between two functions, if you were to compute it brute force for each, so it's basically, the pointwise product of two functions and integrating over that. And then I shift that one function again and do the same thing again. Now that would be L squared time if you do it in the original representation. However, what you can do is you perform the Fourier transform for each of the components, right? That's L log L time. Again, L log L. You pointwise multiply, that's order L. You then perform the inverse Fourier transform, and you get the entire convolution in L log L time. So you've seen something like that when you have band diagonal matrices. Or if you want to do convolution image. So you've probably used some smoothing filters in Photoshop or GIMP or something like that before, right? What they actually do behind the scenes is they transform into Fourier space, Fourier representation of the filter, they run it over it, and then they inverse Fourier transform it. That's what happens behind the scenes. So this is really, really useful in practice. So basically, band diagonal matrices, you can perform very fast multiplications. Convolutions, you can do them very rapidly by exactly this trick. And these methods have actually revolutionized a number of areas of essentially analysis and theoretical computer science. So look for things like the subsampled random form. So there's one paper that's really cool by Chastel and Ailon. Thanks. I think so. 2007 or 2000. It's either 7 or 9, and it's basically about the fast Johnson-Lindstrauss transform. What I'm talking about today is easy, but it's a paper. Okay, so now why do I go harping on about the Fourier transform? Well, because we're actually going to use it. We're going to use it to prove things about distributions. And so there's this one tool, it's called the characteristic function method. And basically, it's just, well, doing Fourier transforms on distributions. That's all it is. And then it's basically Fourier analysis of distributions and proving that certain things hold that are really easy to prove in Fourier domain and not so easy to prove in the original domain. So the first thing that's really useful is that the sum of two random variables is a convolution. We know that, right? So you can just work it out, right? Because if I have p of x plus y equals z, then I have to integrate out over p of z minus y times p of y, right? Because these two have to sum up. And that's exactly the convolution. So now I use the formula from the previous slide, which is, well, the Fourier transform, so the characteristic function as we're going to call it now, is therefore the product of the characteristic functions of each of the random variables. Yeah, I'm skipping constants, yes. Actually, why can I be lazy and skip constants here? Why can I do this? Yep. Perfect. Because I know that the integral is 1. So this is something that you do also in message passing, that you don't worry about the normalization constants until the very end. You just save a lot of computation by being lazy and not worrying about the normalization until you really need it, and only then you compute it, and quite often at that point it will have become a lot easier.
Where is the constant being
Yeah. So depending on how you define the Fourier transform, you might have a two-part. Yes. I'm just being sloppy here. Okay, now, and a really cool other thing is that the Fourier characteristic function is unique, and that's just from the fact that, you know, it goes to bijection with a Fourier transform. Yeah, okay. So, weak law of large numbers. Let's prove that. So, what I require is that the expectation of a random variable exists. That's all I need for that. Okay? And so now I'm going to do the following thing. I'm just going to compute, you know, the Fourier transform. And I'm actually not going to explicitly compute it. I'm going to perform a Taylor expansion. So I know that e to the I omega x is 1 plus I omega dot x plus some term little o of omega. Right. That I know because, well, that's just, you know, the exponential function is analytic, so this is very easy. So therefore, the Fourier transform, which is just the expectation of this thing, is 1 plus I omega dot the expected value of x plus some little o of omega. With expectation just goes through. And yeah, okay, we need to be able to bound that tail, and that's fine. Now, if we have many random variables, then, well, what I get is my expectation, of course, goes like, you know, 1 over m. I get the same term here. And so I have 1 plus I over m omega times mu, and little o of omega divided by m raised to the power m. So this term in the limit will go away. This term here, and this will disappear faster than this one too. So now, well, we know what the following term is, right? We know that 1 plus, you know, 1 over n raised to the power n converges to e. We know that, right? So sometimes you actually define e to be that limit. We also know that 1 plus c over n to the n converges to e to the c. Our c is exactly omega times mu. And so if we look at this limit, we can see that this converges to e to the I times omega times mu. So what we've just done is we've computed the Fourier transform in the limit, which turned out to be easier than computing the Fourier transform of each of those random variables on its own. Because this y went away. It went away faster than this term here did. So I only had to worry about this. And now, well, that is exactly the constant function. That's the Fourier transform of the constant function. So I've just proven that in the limit, the characteristic function of the average is the characteristic function of the constant function. Easiest way that I found of a lot of other tools that take a lot more than 4 equations. So that's why I picked this one. Okay. Big warning. the moments need not always exist. So for instance, if I have a Cauchy distribution, which goes like 1 over 1 plus x squared, computing the mean would require that this integral here exists. Minus x's, but you can get any numbers by being clever about the integral boundaries, right? So that's the integral here. It's x over 1 plus x squared, and that's bounded from below by the integral going from 1 to infinity of 1 over x. And yeah, that's obviously bad because it diverges. So this is a distribution that doesn't even have a mean. For that distribution, I can't get that previous result, right? Because this thing up here is not well defined anymore. So it's just a bit of a warning. Okay. Now, the second thing that we're going to prove is the central limit theorem. I know this is math after equation after equation, so, but this is probably the hardest class. Okay, so in other words, it's going to be easier from now on. So the next thing is the central limit. It's also one of those really cool theorems to prove. And again, we do the same thing as before. We compute the characteristic function. So I have 1 plus I omega x minus 1/2 omega squared x squared plus then some high order terms. Now, if I subtract out the mean, the linear term in x goes away. So I just have left the 1 plus 1 minus omega squared x squared plus some high order terms. This is, of course, then the variance, right? That's all I'm left with. And so, by normalizing suitably, this is the sum over these random variables. So I use the convolution theorem. We get that by averaging over m terms, so m equals n on this slide. Sorry about that. This is the quantity of which we need to take the limit. Because now we average over those, right? So we have this here, the term. And now, again, we use the same exponential limiting procedure. So that same equation that we had here, just that now our c equals, omega squared. So 1/2 omega squared. Pardon? Don't have that missing because this will grow with the sample size. So that's where your 1 over m goes. Well, I mean, this is exactly the point. You don't normalize by 1 over m, but you normalize by 1 over square root m. That's exactly why you get this nice rate. So the thing is, to show that this is well behaved and converges to the normal distribution with zero mean and unit variance is a stronger result than showing that the 1 over n average will converge. Okay, let's work that out in detail because I guess then I didn't explain something very well. Let's make our life really easy and assume that all the sigma i's are equals to sigma. So sigma I equals sigma, and further all mu I equals mu. So Zn is therefore sum over xi minus mu divided by the square root of n times sigma squared, right? So this is 1 over square root n sigma inverse, and then here you have the sum over I going from 1 to n xi minus mu. Okay, let's write this out as an average, right? So I can write this as 1 over n here, and I need to multiply here. Okay. So what I therefore have is that I have square root n over sigma times the average sum over I equals 1 to n xi minus mu. And I know that this here converges to a normal distribution with zero mean and unit variance. I mean, this is basically what we're proving. Right. So this n term here scales this entire the deviation of the average from the mean up, right? It scales it up by square root n. And what I'm showing is that this, ever more blown, difference between and, the property. So that this has a limit distribution that doesn't change anymore, right? That's basically a normal distribution with zero mean and unit variance. So this is different. So that, because the thing is, if I was to divide by n overall, this would basically mean that I would get like a normal distribution where the variance goes to 0, right? But that's not well defined in the limit, right? I mean, this is just like, well, it'll converge to the constant function, but what are the deviation properties in the limit? So this is why you need to essentially keep on magnifying the imperfections, so the deviations from the average, such that I can actually still make a statement in the limit about it. So that's a rather subtle point. Sorry, I glossed over it a little bit before. That's a very good question. Thanks for asking. Yep?
So I think the concern was the summation of xi does not go to mu I, right? It is a 1 over n summation of xi which goes to
Okay. Bracket. I assumed, because I have an index I here, that it's essentially using Einstein notation, as in whenever you have an index, you immediately assume that it's inside a sum of over which this goes. So I was being sloppy by not putting a bracket here. Yeah, that's really what it is. Okay. Now, okay, back to this. So what we have here is we normalize suitably, we get this quantity, right, because we have, the complex conjugate. And so what we get is that the Fourier transform is e to the minus 1/2 omega squared for sample size going to infinity, which is a Gaussian, right? Now, those of us who've done Fourier transforms know that the Fourier transform of a Gaussian is a Gaussian, right? Which is awesome. More specifically, for a Fourier transform with unit, I get a Fourier transform. I get a univariate Gaussian again, and that's all I need. Because now I just transform, and presto, I know that in the limit, my average converges to a normal distribution with zero mean and unit variance, which is exactly what I wanted to show. Done. So the really cool thing is, without looking at a lot about the function that I'm analyzing, but only by, in this case, by already subtracting the mean out, they will be well behaved when they converge. So after all this theory, let me show you some pictures. Question?
So I still don't get why. Can you go back one slide?
Okay.
So this limit you work for n go to infinity. So have this.
Okay. So why? So does this hold?
Why that means that it's normal distribution.
Oh, okay. So first of all, the reason why this holds is because this will go to 0 faster than this does, right? So therefore, I can ignore this and just take the definition of the exponential. Okay. Now, what I have here is therefore the Fourier transform of a distribution in the limit will be a Gaussian, right? Now I just apply the inverse Fourier transform. And this allows me to get the original function back.
So this means that the variance will be 1.
Correct. Correct. This means that it has, this corresponds to a distribution with 0 mean and unit variance, a Gaussian. And that's all I wanted. Remember? Here, I want to prove this property. And what I've done is I've taken the Fourier transform of this and shown that in the limit of n going to infinity, the Fourier transform of this converges to the Fourier transform of that. And since the Fourier transform is unique, I therefore have just proven that those two things are the same. It's just much easier to do in Fourier space than in the original space. So doing this in the original space would be many pages of work. Here it's basically 3 lines and a bit of hand waving. Okay. Let me show you a few pictures. So basically, let's say I take a random variable which has, takes on values uniformly between -12 and between -1 and 1. It's a uniform distribution. And well, okay, I kind of cheated here. Well, this is normalized wrongly. It should be, obviously, 1/2. But okay, so I hope you excuse me for that. Then I've added them together, so I convolve it. And as I keep on convolving, this, of course, gets shallower and shallower and wider, right? Now, if I was to go and, rescale this properly to, be, basically have, integral 1, then and basically, unit variance, then as you average more and more, you see that this will start looking more and more Gaussian. As a matter of fact, if you squint at this here from really far in the last row, and I told you this is Gaussian, you would probably believe me. Maybe not in the first row, but in the last row you would believe me. So what we've just shown is that even already the average over 5 random variables, in practice, for I have distribution, Gaussian. This is sometimes because now something that has bounded range. Okay. This is effectively what the central limit theorem will tell you. Now I'm going to conclude with some you deserve the break. No, actually, I should probably not do that because Josh needs time to hand out the exam.
So do you want to stop here?
I'll stop here, and we'll do this on Monday.
Okay. Can we get the TAs up here to help hand out the exams?
Did you stop the video? Did you stop the video?
I sent you would you put up the email with the link?
Okay.